Mr. Ayman, if it's okay for you, we can start, I guess. So, good evening, everyone.
Okay, let's go.
Good evening, everyone. My name is Elçin Süleymanzadeh. I am treasurer at SP ASOIU student chapter. Today, I will be moderator for this session. Our session today is about progressive cavity pump system. And our honorable guest today is Ayman Allam. Mr. Ayman has over 13 years of experience in oil and gas industry. He has started his career as production engineer in Dara Petroleum Company and has experience as artificial lift field engineer leader in AlKhorayef Petroleum Company and more than a year of field supervisor experience in the same company. Now, Mr. Ayman is Petroleum Engineering Department Head at Dara Petroleum Company. Thank you, Mr. Ayman, for accepting our invitation and helping to develop our community. Floor is yours.
Thanks, Elçin. I would like to say hello to you and everybody and good evening. I wish you all are doing okay. Our webinar today will be about the progressive cavity pump. It's gonna be around 1 hour. As you know, 1 hour will not be enough to say everything about PCBs, but I will try to give you as much as I can during this interview. I wish you all get some valuable information and help you in your future. Let's go quickly. We will talk quickly about the artificial lifting system. When do we need to put a well on artificial lift? Difference between the different artificial lifting systems available today in the market, advantages and disadvantages of PCB compared to others. Then we will talk about the system components. I will be talking in kind of detail. I want everyone to understand the function and the component of each component in the PCB. It's very important to you to understand how it works. Also, we'll talk about some pump fundamentals, understand how it works. We'll talk about the design, how we make full system design. And I also have some screenshots from a real case. We will also talk about the installation steps, precautions, and I have picked also one of the most famous troubles in PCB system, and we'll see together how we can solve it. Okay. Let's talk in the first about PCBs. PCBs were first seen in the 1920s. At that time, they were initially used in surface transfer purposes. Then it started to enter the oil market in the 1980s. And it was first seen in the oil field by around 20 or 25 years back. As you know, during the well life cycle, in the beginning of the life cycle, the formation pressure or the reservoir pressure is almost still high. So it can lift the formation fluids from the formation depth up to the surface at an enough pressure to reach the production facility. Then, as time goes on, this pressure will decline and production starts to decrease. And we will search for alternatives to maintain the reservoir pressure, either through gas injection or water injection. Then pressure will continue to decrease actually. And then we will need to put the well on an artificial lifting system. We will certainly need the artificial lift in cases of a dead well. As you can see here, the bottom hole flowing pressure is less than the hydrostatic pressure plus the surface pressure plus the anticipated losses. Only the well can produce at the surface. Otherwise, the well will be dead well, because there's, as I said, the flowing pressure will be less than, sorry, I missed it. If the bottom hole flowing pressure is more, then the well can produce. Otherwise, it cannot produce. Actually, this one should be reverted. Sorry for this. Let's understand. Second case where we will need artificial lift if the well is already producing, but we do need to increase the production rate. Okay, so the decision is now taken to put the well on an artificial lifting system. We do have plenty of systems. We do have the ESPs, the gas lift, the reciprocating rod pump, the BCBs, the plunger lift. So which one should I select? There are actually several factors to select the optimum artificial lifting system. For example, if we are looking for a high rate, we will be looking at the ESPs. If we do have high gas oil ratios, we will go to the gas lift. If we are talking about 5,000 barrels per day or less, we will be talking about reciprocating rod pumps and PCBs. The experience of the workers in place will play a big role in the selection. For example, if I have a team which have experience in reciprocating rod pump, the maintenance of the pumps, installation and maintenance of the surface units, I can't be go to ESP. Gas lift, for example, will require compressor gas source, which will not be available all the time. Going back to the previous equation, we said if the hydrostatic pressure plus the surface pressure plus the anticipated losses are less than a bottom hole flowing pressure, the well can produce, otherwise it cannot. So all the artificial lifting systems will be working on increasing the bottom hole flowing pressure. How can they do that? By adding energy actually to the reservoir. Again, how this happens? Any mechanical pump like the PCB or the reciprocating rod pump or even the ESP, they reduce the intake pressure at the pump intake and increase the pressure at the pump discharge. So bottom hole flowing pressure will be now high enough to beat the losses, the hydrostatic head and the surface pressure, and thus the well can produce. Only gas lift will be working on the hydrostatic pressure, where the injected gas reduce the hydrostatic head of the fluid column. So using the same bottom hole flowing pressure, it can beat the summation of those three. I hope it's clear now. Today, as you know, we'll be talking about the PCB. Okay, what are the advantages of a PCB pump? The first of which is handling high viscosity fluid. When we talk about high viscous fluid, and I mean low API fluids, PCBs pop up as the best solution to handle high viscous fluid. I do have some fields here running with PCBs and oil API 11 API. Cannot imagine, it's just as thick as grease, actually. PCBs are running very efficient in those fields. By the same time, Others, other systems like jet pumps and sucker rod pumps stuck in a minute and sand handling. The same concept of high viscosity, also BCBs are the best artificial lifting system to handle high sand cuts. And when we talk about sand, I don't only mean the formation sand, but also the artificial sand, like the sand used in the hydraulic fracturing jobs. After the hydraulic fracturing jobs, high sand cuts are always expected. PCBs can handle this sand very efficient. Other pumps like sucker rod pump will get stuck very quickly and cause premature failures. No valve and no reciprocating parts. The photos in front of you are related to sucker rod pump. This is seat, this is top cage. So as you see, any reciprocating part is a potential failure point. So with the PCBs, there are no valve, no reciprocating parts, only one moving part, and the failure is only limited with some very, very critical conditions. Low capital cost, low power consumption, low maintenance cost, and low design operation. Presentation. In the last few years, as you know, the oil price drops down and everybody is looking for cost reduction. So PCB actually serves very well in this field. The system capital cost is very low compared to others. You will find me, you'll listen, or you'll hear me comparing PCBs very frequently to sucker rod pumps, actually, because both are serving in the same production range. We are talking about 2,000, 3,000, 4,000 barrels per day. So if you want to produce certain volume using PCB, I can say that the capital system cost may be around 50% only of the capital cost of a sucker rod system to produce the same rate. Also for the PCB, it has a very low power consumption. This is due to the constant current from the power source. In the sucker rod, as you know, the reciprocation movement causes like wavy current consumption, which is translated to high power consumption. Also, the PCBs have a very low maintenance cost related to the others, like gas lift or other types. Design flexibility. Actually, as we will see later, with a very simple button, you can speed the pump up or slow it down according to the conditions, which are updated every day and every hour. Maybe in the beginning of a new well, you make the design to produce, let's say, 1,000 barrels per day. After some time, the fluid level drops down and you have to slow it down. So it's just simple turning a button to reduce the speed and reduce the production. That's it. Low surface profile, which suits the offshore areas and high sensitive areas. It's also applicable in the deviated and horizontal wells. And it has a very high system efficiency. The PCB system efficiency can reach up to 75%. This is due to several factors: small motors, low power losses. So for other systems, it may reach only 40 or 50%. So it's a bigger advantage actually in the BCB. Same as other systems, every system has its advantages and disadvantages. BCB also has some limitations. The first is the limited production rate, as we say. The typical production range for PCB is around 3 to 5,000 or less, far away from ESPs. ESPs, we can talk about 15,000 or even more, up to 25,000 barrels per day. Second limitation is the limited bump depth. As we will see later, the BCB system utilizes a sucker rod string, which is a steel rod string connecting the surface component down to the pump, let's say at 5,000 feet. So you can imagine to rotate this sucker rod string, steel sucker rod string, how much power you need at the surface. So the more depth you go, the more sucker rod string and the more power at the surface. Also, by increasing depth, actually the temperature may go up, and we will have a certain limitation, because the most famous and the most commonly used PCB today in the market utilize an elastomer or rubber stator. So it has a rubber element. This rubber element will swell or overswell in high temperatures. The typical temperature or the maximum temperature we can reach using a rubber elastomer, we can say around 150 Celsius. However, some new technologies can reach up to 450. Those are called metal-to-metal PCBs. So the rubber element is now replaced with a metal elastomer. So sorry, with a metal stator. Rig will be required to replace the pump in case of tubular pump. As we will see later, there are some classifications for the BCBs. Some are tubular pumps, some are insert. The tubular pumps, that the stator will be connected to the tubing string. In this case, rig will be required for servicing or replacing the pump. And to be honest, this is the most commonly used type. Minimum fluid level requirement. Again, talking about the rubber elastomer element. This rubber elastomer element must be always covered by fluid level to cool and lubricate the rubber elastomer stator. Otherwise, if the pump runs out of fluid coverage, it will be called the bump off condition. There will be no cooling effect, so the pump will overswell and will be burning. Okay, now let's talk about the BCB components. As you can see, the full system here, if we classify it as surface components, including all the components above the surface, and downhole components just lying below the surface. The first component is the electric panel. We have two basic types of electric panels. We have fixed speed controllers and a variable frequency drive. The fixed speed controller, just like an on-off controller, it protects the motor against the disturbance from the power source. That's it. It's just like on-off. There is no any means to control the speed, no speed up, no slow down. It's not too much used because, as I said, it just controls the current from the power source and protects the motors actually, but no means of controlling the motor frequency, no control for the pump speed. The other side is the variable frequency drive. It's just also known as VSD, variable speed drive or variable frequency drive. Those can provide the function of controlling the motor frequency and consequently the motor speed, the pump speed, and the production rate. So the function of both will be protecting the motors against disturbance of the power source, control the motor speed. Also, they will both allow monitoring of the well parameters. It's very important to monitor the operating parameters along the life of the system. As you see here, the panel is showing the speed, also the current, also the torque. Those parameters tell you how the pump is working down in the well. Well monitoring also is very, very important issue. It's always important to record and monitor the current and the torque. Those will tell you how the rotor is turning inside the stator, what kind of friction is going in between the rotor and the stator. The next component will be the drive head. Types of the drive head are, the first type is the direct driven. Those will utilize electric motors with certain kinds to transmit the power to the rod string. As you can see, there are two basic types of drive heads: single motor drive heads and dual motor drive heads. Of course, the dual motors will be used to supply more horsepower, which will be required in high torque applications, high depth applications. Next type is the hydraulic driven. The hydraulic driven types will be utilizing hydraulic motor connected. This hydraulic motor and the hydraulic pump will be connected through this hose to rotate the hydraulic motor, and the hydraulic motor will be rotary motion will be transmitted from this motor to the polished rod through set of gears or pivots. Last type is the gear driven. Those will be utilizing kind of gearbox to transmit the rotary motion from the motor to the polished rod. Functions of all types are almost the same. They all suspend the weight of the sucker rod string and provide the necessary rotation to the polished rod, provide the necessary torque, which is necessary to rotate the sucker rod string and the rotor inside the stator at the needed speed, allow safe release of energy during the normal operation of the BCB. Energy, or huge amount of energy, we can say, is stored in the sucker rod string in form of torsional energy. When the well is stopped, even planned or unplanned, planned I mean for maintenance or for any other purpose, when the well is stopped, the stored energy will be released suddenly. If this release is uncontrolled, the rod string will rotate in the reverse direction at a very high speed. Being uncontrolled can really cause serious damage for the equipment, can even cause some personal injury, can even cause personal injuries. The last function is that they all prevent the leakage of the well fluid. This part is called stuffing box. We will see later. It forms a kind of seal around the polished rod and prevents the leakage of well fluid. Let's go into the drive head itself components. As we said, this is the motor sheath and this is the drive head sheath. The rotary motion is transmitted from the motor sheath to the drive head sheath through a set of belts or through a gear transmission. The second component is the thrust bearing. Function of this thrust bearing is to allow the rotation of the rod string while suspending the axial loads. Brake system, as we have just mentioned, this is an example of uncontrolled backward rotation during backspin. That was uncontrolled release of energy. Several types of brake systems actually are there in the market. Hydrodynamic systems, gear pump brake system. The one in the photo is a caliper brake disc brake system. Actually, it's the same as the one used in the cars. This is also we can say it is the most commonly used system actually. All will have the same function to control the speed of the backspin during shutdown. And the stuffing box. As we said, the stuffing box will allow to seal around the polished rod and prevent the leakage of fuel fluid. By tightening this cap, the cap will compress those rubber elements against the polished rod and prevent the leakage of fuel fluid. The last component in the surface, above the surface, is the pumping tee in the rod BOV. The pumping tee will allow a path for the fluid from the well fluid coming from the downside to the flow line. And the rod BOV allows it utilizes those strands to close around the polished rod and secure the well for any maintenance work on the surface drive head or to secure the well for any purpose. This one you see in this photo is just a composite BOV. It just gathers the two functions together. This is the flow tee and those are the BOV rams. So they are now integrated in one piece, as you see in this photo. So now those are the surface components, the electric panel, the drive head, and the composite BOV. Now let's go to the downhole components. First, we'll start with the rod string. The function of the rod string is to transmit the rotary motion from the surface component at the surface from the drive head exactly and deliver the rotation to the rotor down inside the stator. There are several types of rod string. The most commonly used one is the steel sucker rod. They are also called the conventional sucker rod. The fiberglass rod, which is invented to provide the advantage of lightweight and consequently reduce the power requirements at the surface. And the continuous rods, which are commonly known in the market as core rods. Those are also steel rods, but spooled, as you can see, and mounted flat. So the whole well can be only with two connections only, one at the surface and the other just above the rotor. As we said, the most commonly used is the steel sucker rod. A conventional sucker rod string will consist of polished rod at the surface, steel rod with chrome-plated surface. Just the smooth surface will be required at the surface to provide the necessary seal with the stuffing box to prevent any leakage. Then we will have full-length steel sucker rod, pony rod, just like the full length but with shorter sections, and coupling to connect the sucker rods together. The steel sucker rods are available in so many grades and sizes. For example, the ABI grade will suit the low load application. K will be suitable for cruises environments. D, we can say for medium to high loads. Also, some manufacturers provide some special grades like the EL. This is Weatherford, I think. Provides high torque. And the 97 of Norris also is a high strength sucker rod. All manufacturers provide sucker rods in 5/8, 3/4, 7/8, 1 inch, 1/8, and 1/4, and lengths 25 and 30 feet. And the downhole pump. This is actually the heart of the system. It consists of two main parts, the stator and the rotor. The stator is the stationary part of the pump. It consists of steel pipe and rubber elastomer, and they are both bonded together using a bonding material. The stator is a double helical shape, okay? The same as the helical design of the rotor. Remember that PCB always come as a pair of stator and rotor. We cannot exchange rotors between different pumps because the rotor and the stator are designed to match each other. The rotor is a stationary part. This one you see in the photo, this metal one. It's steel piece, helically machined and covered with chrome, and it rotates inside the BCB and causes the fluid to move from one cavity to the next. So thus, getting the fluid from the pump intake at the bottom and delivering it upside toward the production tubing. How can we identify pump? Actually, according to the API pump designation, the first two digits in any pump serial number will refer to the pump production rate or the pump displacement. Let's be more specific. Pump displacement. In this example, as you see, this is a 98 series pump. This means that this pump can produce 98 cubic meters per day per 100 RPM. If this pump is running at 200, we will be predicting 196 cubic meters per day, and so on. The next number, the next four digits, will be referring to the pressure development, the maximum pressure rating for this pump, which is 1800. This refers to this pump can lift the fluid 1800 meters from the pump depth up to the surface. This is the maximum height the pump can lift. The next few digits refer to the stator serial number, and the next are referring to the rotor serial number. The next will be referring to the elastomer type. Each brand or each manufacturer has certain types of elastomers, so this should be also clear in the pump serial number or in the pump designation part. You will find the serial number for each pump near the top section of the pump. So all the previous, those were the essential components. You can never run a well using PCB without any of the previous parts. The next will be accessories. They are used to provide some extra functions. Some will be necessary also according to the situation. The first component is the tubing drain. Well, let me show you this. In some cases, we just seen the rotor and the stator. In some situations, the rotor becomes stuck inside the stator. This means if the well was producing, the tubing string will be full of fluid from the pump depth up to the surface. We are talking about 4,000, 5,000 feet, so we are talking about more than 30, 40 barrels. If the rig just proceeded to put the tubing in this situation, this means we will be having 30 or 40 barrels on the ground, which is the real mess. This will be projected and be like you may take a breach in that. So it's necessary to find some way to drain the fluids inside the tubing string into the annulus. The tubing drain actually provides this function. As you can see here, the one in the photo has the tubing opened. Okay, this is a hydraulically opened tubing drain valve. This cap originally was set here, covering both holes, and by applying certain pressure, some shear pins installed here are sheared, and thus the cap slides on the sleeve and now the holes are exposed, so the fluid inside the tubing can now be easily drained inside the casing, and then you can pull the tubing out safely. To make it clear for you, let me show you this. I hope this can be clear for you. Okay, this is the casing string. This is the tubing string, and the stator lying at the bottom of the tubing string, the rotor inside the stator, okay, connected to the sucker rod string. In case of the stock, we are expecting this portion to be completely blocked. I hope it's clear. So this now is blocked, and the tubing is full of fluid up to the surface. Those are the 30-40 barrels we are taking care about. And this is the tubing drain. Actually, it's normally placed one joint above the stator to provide the necessary connection to the casing to drain the fluid inside the casing. So that was the tubing drain. The next accessory is actually the no-turn tool. It's also referred to as NTT or torque anchor. I can say actually this is a very necessary component in almost all applications. The no-turn tool, as you know, now the rotor, in order to produce, the rotor is rotating inside the stator. Okay, the rotor is connected to the sucker rod string, and the stator is connected to the tubing string. So while normal operation, as the rotor turns, there will be some potential, the tubing also rotates. If that happens, there is a big risk to get the tubing backed off or unscrewed. This is a big failure. We don't want it to happen. So how can we stop this? Using the NTT. Actually, the blocks, drag blocks on this side or almost on the all side will bite against the casing inside wall and prevent the tubing rotation. Gas separator. Gas separator is almost installed below the stator. It prevents the free gas from entering the pump intake. The concept the gas separators are working on relies on forcing the fluids to repel or to move in a circular path, and use the concept of let me remember that. Centrifugal force. Use the concept of centrifugal force to repel the free gas outside, and then the free gas can exit from that hole outside to the casing and not enter into the pump intake. Rod centralizers. Those will be very, very important when we are designing or running a hole in a deviated well or crooked or horizontal well. Those will help the sucker rod to be centralized inside the tubing string. Otherwise, the tubing string will rely on the backside of the tubing, and the friction between this metal sucker rod to the metal tubing will cause high friction. I can say it clear, it will eat the tubing wall and cause premature tubing failure or sucker rod failure or even both. So rod centralizers are very, very important in horizontal or deviated wells. Downhole sensors. Those are the smart tools actually used to monitor the downhole pressures. Normally, there will be one port here to sense the pressure inside the annulus. Normally, downhole sensors will be installed just above the pump to measure the pressures at the pump discharge and also almost at the pump intake. It's just the length of the pump. So downhole sensors, it has two ports, one at the outside, and the second hole will be here. This one connected to the tubing, so it senses the pressure at the pump discharge, and the outside hole will be sensing the pressure inside the casing, the intake pressure. So those are very important in monitoring the well, are very, very helpful during troubleshooting, and also they can be connected to the VFD or the electric panel and allow some advanced applications in cases like the pump is pumped off, there is no fluid level, the intake pressure is not enough. You can easily programize that on the VFD to take an automatic action, reduce the speed as the fluid level drops below certain value, and then speed up again if it exceeded that value. So very smart and very useful parts. So let's recap the system components. Electric panel, drive head, BOB at the surface, sucker rod or rod string, and the downhole pump below the ground. Now let's see this quick animation. Okay, this is the drive head stuffing box, the electrical motor, and this is the polished rod passing through the drive head and going down into the well. This is the casing. This is the casing, this is tubing, and this is sucker rod string. And this is our downhole pump. As you see, this is the stator and this is the rotor. And this is the tag bar I will talk about just after the video. Now, when we start through the electrical panel, the motor will start to rotate, drive the polished rod and sucker rod string to rotate. Sucker rod is transmitting the rotation into the rotor to rotate in the forward direction and suck the fluid from the pump intake and force that up to move upward inside the stator and then into the tubing string. Fine. Let's talk about some pump fundamentals to understand also how it works, and talk about some formula. The loop ratio. The loop ratio is the ratio of the rotor loops to the stator loops. As you can see here, this is the rotor. This is a cross section inside the pump. This is the rotor and this is the stator. Rotor is one loop and the stator has two loops. The reason the stator has one loop more is just to drive the fluid, provide some space from the fluid to move from downside up to the upside toward the tubing. Also, 2 to 3 applies the same concept, 2 rotor loops to 3 stator loops. Always the stator will have one loop more than the rotor. Most of the pumps today in the market are of 1 to 2 ratio. Some are 2 to 3, but the higher ratios are never seen in artificial lift. They are used, but in surface transfer applications. Eccentricity. Eccentricity is the difference between the stator center line and the rotor center line. This is stator, and this is the stator center line, and this is the rotor center line. and eccentricity is the distance just between poles. In this case, in the picture in front of you, this is a 1:2 loop ratio pump. This is a special case where the rotor major diameter and the rotor minor diameter, the difference between them, you can divide it by 2 to get the eccentricity. But the same as I said, this is a very special case to the 1:2 loop ratio pump. Pitch length. The stator pitch is always also double the rotor pitch length. Eccentricity and pitch length controls the pump geometry. For the low eccentricity pumps, we can say those can suit the high water cut application, high production rate, and low viscous flows. Unlike the high eccentricity pumps, those will be more suitable for the high viscous flows and high sand or sediment produced. Pump displacement. Remember the 98 that we talked about just a few minutes before? This is the formula that controls that number. The pump displacement will be equal to the rotor minor diameter multiplied by the eccentricity multiplied by the stator pitch length. C is a constant which changes if you are going to use imperial or metric units. To compute or to calculate the production rate or the flow rate, you will have only to multiply the pump displacement and multiply it by the pump speed in terms of RPM. Pressure development, which is the second important feature you must know about your pump, which is the pressure development. What is the maximum pressure that the pump can withstand? Actually, this pressure is differential pressure between pump discharge and the pump intake. Again, on the same drawing, as you can see here, this is the pump. Just above the pump, this is charge pressure, and this is pump intake pressure. This pump intake pressure, and this is the pump discharge pressure. Each pump can only withstand some certain differential pressure. What controls this value? Actually, the pressure seal lines control the value of the rated pump pressure for each pump. Pressure seal lines are formed by the physical effect of the rotor against the stator. Only fact and pressure development pressure or the differential pressure, the more or less pressure seal line, and consequently so that are all the basic pumping fundamentals. Now let's talk about the system design. The target of any design is to achieve the target production rate and ensure optimum performance and run life. When we talk about optimum performance, let's say an example. We need to produce a well with 1,000 barrels per day. We can achieve this 1,000 barrels per day using 4, 5, 6 systems. We can use very big pump, very huge drive head, and then start the well. We will get, sorry, what's that? We can use, like I said, several systems. Which one is the optimum? The one which has optimum power consumption and optimum pressure rating for the pump, optimum torque loading for the sucker rod string, and optimum motor sizing at the surface. Also, the run life is very important. Like we said, for example, in the deviated wells, if we neglected using the rod centralizer, we will have a very premature failure in the rod string or the tubing, which is not acceptable. And the economic considerations are also very important. Remember, the cost reduction is just chasing us. In order to get a successful design, some information must be available and accurate. Information about the wellbore geometry. We need to know the wellbore, is it vertical or horizontal? If it's horizontal, we need to know the kickoff point, inclination, azimuth, versus depth over the whole length of the well. We will also need to know the casing size, grade, ID, and we will also need to know more about the production conditions. We need to know the wellhead pressure, the expected well or the needed wellhead pressures. Remember that you will need the well to produce a certain pressure so that the fluid can reach the nearest production facility or process. We will also need to know about the wellhead temperature. We need to know about the fluid properties. What kind of fluid we are expecting to produce. Remember, the elastomer is just waiting to deal with the fluid. It cannot. The elastomer designed for normal applications cannot withstand H2S or high aromatic content fluid. We need to know the water cut, the sand cut, viscosity, density, aromatic content, H2S, carbon dioxide. So all these must be known. Design softwares are not so much for PCBs, and Separator is the most commonly used one. Before going to design, we just need to highlight a very, very critical and important topic, which is the elastomer selection. When a new manufacturer or supplier is going to have a project in a certain field or well, fluid samples from that well or field must be taken, and then the supplier tries all the elastomer types available against the fluid sample to determine the most suitable elastomer type. As I said, elastomer specimens will be inserted in the fluid sample and all together put inside this device, which is called autoclave, to do the fluid elastomer compatibility testing. Testing may last for 3 days or a week to determine the most suitable elastomer type. And after the test and the change is put on a graph to find the best elastomer. In this example, B will be the best because it has exhibited the least volume change. So this means if this elastomer type is inserted or used as an elastomer type inside the pump and run into the well, it will have the less swelling effect. This photo is well known. This phenomenon is known as peanut. Originally, the Stator elastomer had that shape, and due to misdesign, the elastomer overswelled, and this is for sure caused more friction with the rotor, and this is translated into higher torque at the surface and complete stuck at the end. Those screenshots are from the Separator software. In the first tab, you will be inserting your wellbore geometry. Then in the equipment configuration, you will be choosing your artificial lift type. Is it PCB or ES PCB? By the way, ES PCBs, it's conventional PCB, but it's just running without sucker rod string. It has an electrical submerged motor, same as ESP. So you can say this system is just a mixture between PCBs and ESP. PCB pumps, stator and rotor, but the motor is downhole instead of at the surface, with electric motor running from the pump depth up to the surface and connected directly to the power source, same as ESP. So go back to our conventional PCB. Here you will be inserting your drive head specifications, brand, belt ratio, electrical motor size, RPM, and horsepower. In this section, you will be adding your casing details, casing string details, the depth, top and bottom, and grade, nominal size, and ID. Same for tubing. In the rod string, you will be adding your rod string configuration. And here you'll be adding the pump seating depth, perforation depth, and pump specifications. Remember, C-fair design. It's just like try and error. You will have to put your conditions. Conditions are always unchanged and uncontrollable. You just add your fluid properties, operating conditions, and try different systems till you get the most reliable configuration, which gives you the target rate at, like we said, target rate, optimum run life, optimum performance. Fluid properties. In this section, we'll be adding the water cuts, sand cuts, gas gravity, oil API, viscosity, and you will be specifying you need your design to be based on the target rate or the pump speed. Submergence means intake pressure or the fluid level, and specify the temperature at the bottom hole. Then you just press calculate, then C-fair will come out to you with the result. We will need to check our pump pressure loading. In this case, it's 83%. I would say it's a little bit high, but it's acceptable. Maximum rod torque, 266. We'll just need, in this case, to revise the rod string grade that we used in this design and check 266, is it okay or is it overrated? Maximum load connections, 0, which is pretty good. Truss bearing life, 18%, which is also very good. Years, sorry. Okay, now we have selected our system components and made the design. So it's time to install the pump. We said the pump consists of two main parts, stator and the rotor. The stator is run as an integral part with the tubing string. This is a typical sketch for the well. If we started from the downhole, we'll find the mule shoe, gas separator, and torque anchor, and the tag bar. By the way, I forgot to talk about the tag bar. This tag bar is like a joint, which is installed just below the stator, which has a pin, okay, stop pin like that. It's very important during the rotor installation to space the rod, to place the rotor in the desired location inside the stator. We will talk about this in very few seconds. Then let's go back to the tubing sketch. Then the stator and downhole gauge or sensor. Then tubing, one tubing joint. Then tubing drain valve. Then tubing to the surface, controlling the depth at where we want to set the pump, and then the tubing hanger. As you can see, the serial number is mentioned here. It's very important to mention the length, the OD, the ID, the serial number for each and every part you run inside your hole. This is very important to monitor in the well performance, monitor the pump performance, and intervene the well in cases you need. After we have installed the stator, it's time to install the rotor. The rotor will be run with a sucker rod string at the bottom. Let's see this animation. Is very helpful to understand the rotor space out operation as the most critical operation during PCB installation. As we said, our target is to set the rotor at certain depth inside the stator. Remember the pressure development of the pump. We don't want to lose pressure seal lines. We don't want to run with the rotor deeper and hit the tag bar. This will cause pump failure, more friction, more torque at the surface. So we just need to do a perfect space out job. Let's see this animation. Sucker rod is running from the surface. Rotor started to show up at the downhole pump. Here we stopped. You can, at this, once the rotor reaches the top of the stator, you can easily check that on the Martin Decker of the rig itself, or Martin Decker is the weight indicator. You can easily see a drop in the weight because the rotor will rest on the top of the stator. So you can easily see a little drop on the Martin Decker. Then continue to run the rotor inside the stator. And as you see or notice, the rotor is now running slowly. This is very precautionary action when you run the stator inside the rotor inside the stator. Then you will continue running till the rotor reaches the tag bar. I hope you can see this. Okay, now the rotor space out operation will start. Rotor space out means we will take the rotor again up by 2 values. The first value is the sucker rod slack weight. Once the rotor, let's go back to this section. Once the rotor reaches the tag bar, the full rod string weight will now be resting on the full rod string weight will be resting on the rotor. At this point, you will find 0 on the Martin Decker. As we said, space out means we will take the rotor up in the upward direction by 2 values. The first value is the sucker rod string slack weight distance. The distance equivalent to get the full rod string weight. Remember, once the rotor reaches the tag bar, the Martin Decker read 0. And then we continued. But when we make the space out, we just pick up the sucker rod and go in the upward direction till we get the full rod string weight on the Martin Decker. So this is the slack weight distance. In addition, we will pick the rotor up an additional distance. This distance is predefined for each brand and model. Like, let's say, for example, brand X has 100 pumps in the market. Each pump will have certain distance. So now the rotor is resting on the tag bar. We'll pick the rotor up by 2 values. The first value is the sucker rod slack weight and the predefined value. Let's see how this works. Now the rotor is resting on the tag bar. We'll go up. Started to go up by the slack weight. Now we've got the full sucker rod string weight, and now he's picking up the certain distance, and now the pump is ready to be run. As you can see, the rotation has started. Rotor has started to rotate inside the stator and picking the fluid from the annulus and pumping into the tubing string. Thus, we have finished the rotor installation and the sucker rod string. This is a typical rod string sketch. The rotor will be lying at the bottom. And it's also very important to record and report to the rotor serial number, then rotor coupling, pony rods, and sucker rods. Pony rods again for space out, and crossovers to the polished rod. So you cannot see a polished rod at the surface, rotor at the bottom, mixture of sucker rods and pony rods in the middle. Again, your sketch has to include the specifications of every element inside the well. After stator installation and the rotor installation has been completed, now it's time to install the drive head on the surface. During installation, you have to follow up the API recommendations for sucker rod handling and makeup procedures. The wrong procedures will lead to premature rod failures, and those are so many actually. This is like a very huge topic, but it's very critical. You must read about that if you're interested in the API 11 PR. One of the very famous troubles inside with the BCB system is the stuck condition. As we said, PCB is very efficient with the sand production, with the producing flows with high sand cuts. With aging of the bomb, if sand comes as very huge batches, the bomb may get stuck. That means the rotor will stuck inside the stator. And actually, if good monitoring is out there, you can catch this situation earlier before it comes to big problem. As we say, the rotor is normally rotating inside the stator. When huge sand comes in between, this will be translated to high torque. You can, if monitoring is going fine, you will easily catch this on the VFD. Unfortunately, in some cases, bad monitoring will discover the situation very late. So at this situation, the rotor will become completely stuck inside the stator. In this case, we will have to pull the rotor above the stator, pull the rotor out of stator using crane or workover rig, and then flush the tubing string and the stator with flush fluid, and push all the rubbish, all the sand outside the stator, run the rotor back inside the stator, and then start the well. As we said, we'll pull the rotor out, start to pump, then fill the tubing till the fluid reaches the stator. Normally, the flush fluid volume will be around 1.5 the tubing capacity. And remember that you have a rubber element inside the well. You cannot flush by diesel, you cannot flush by chemical. Take your precautions to avoid damaging your stator elastic. Now the fluid washed the stator elastomer and started to build up inside the casing. During this job, there is a very big risk when trying to free the stuck and getting the rotor out of the stator. Once you achieve that, a very high backspin speed be expected. So be precautious, protect your equipment and personnel. Some devices can be used to control the backspin speed. And as I said, the flush fluid, you must take care about the type of fluid you are pumping. And I cannot let this session end without talking about the test bench. It's actually a simulator for the surface and downhole conditions. This is motor, and you can say this is a horizontal drive head, and the rotor is connected to this rod, and the stator is connected to this tubing to simulate the conditions of the well. We use the test bench actually when a pump is pulled out from the well, mainly for failure analysis issues. And you can also use the results to judge if this pump can be reused again or not. We normally make the test at 300, 200, and 300 RPM. The test bench includes closed water system where the pump sucks the water from this tank into the pump intake. Then the pump delivery again discharge the fluid in this tank again. So it's closed circuit. It has pressure sensor, also flow meter to count the pump the displacement rate. And this electrical panel, you can control the test speed and monitor the torque. And that was the end actually of this presentation. I hope it helps you in your future and add to your information. I would like to hear from you. Actually, all your questions are more than welcome.
And there are several questions in chat box. So,
okay.
First question from Ali. He asks, is there any environmental impact of PCP?
For sure. As we said, rubber. Some rubbers are sensitive to the H2S, some others are very sensitive to the high aromatics, some others are sensitive to high temperatures. So as I said also, each manufacturer will have set of elastomer types. Each type will suit different environment. You choose the right elastomer type to ensure your system will operate safely and at acceptable run life for you.
Okay, thank you. Tural asks, what kind of challenges we might face during installation of PCP systems?
During installations, actually, no challenges. The challenges will be during the design stage. If you make the proper design, there will be no challenges during the installation because you cannot, for example, run with a 4-inch and ensure not a challenge. Too much. You also need a big pump, bigger loads. So this is another. So which one is efficient? Electrical submersible pumps or progressive cavity pumps? Same I said. This is completely two different issues. It's just like you have two perfect applications, but each one will be perfect in certain applications. ESPs, we are talking about high rates, light oil. ESPs cannot perform well in viscous oil. PCBs, yes, we are talking about less volumes of fluid, but you can use PCBs in high sand production or in high viscous oil fluid. So it's completely different. You cannot judge which one is more efficient because it's two different applications. I think we missed some questions here, but we need to submit it. Okay. Any more questions? Hello? Hello?
Yes, I guess as it might seem, there is no other questions. Yep.
Oh, thank you all for attendance. Thank you for your questions. My contact info are there in the first slide. I will be happy to receive your questions anytime. I promise to get to you as quick as possible.
Thank you very much, Mr. Ayman. Thank you for your efforts, for your time, dedication for our development and development of our community. Thank you very much. We are grateful to you. So, dear audience, this is the end of our session. You can leave the meeting.